All right, so this applies to both transformers and inductors by themselves. Of course, a transformer basically is two inductors wound on a common core material. And so what we have here in the x direction is magnetic field strength or intensity. Okay, I'll just say intensity. And what we have in the y direction is magnetic flux density, which basically, if I'm looking at a cross-sectional area of some magnetic material, it's saying the density of the magnetic flux lines in through a particular cross-section of that material. And that's relevant for our core material, right? I wonder if I can still paste that figure that I just pasted earlier. No, it's something completely different now. Let me undo that. Maybe I can grab it. So if I were to grab this figure here and bring it over here with us, the magnetic flux is the magnetic field lines, basically, that are passing through this core material, this magnetic material. And so as we raise the intensity of the magnetic field in a magnetic material, the magnetic flux density increases, right? So if I turn up the magnetic field, basically I have more current passing through this wire, I would get a stronger and a stronger magnetic field, and that would result in more and more magnetic flux lines passing through the cross section of this material, right? That makes sense. And so what permeability basically is, this mu, right? We talked about permeability of magnetic materials when we talked about inductors. It basically tells us how much the magnetic flux density increases as the magnetic field intensity increases. And what that is it's basically just the slope of this graph, okay? So as I increase magnetic field intensity, magnetic flux density increases, and that slope is my mu, okay? So I'm just gonna write slope is equal to mu here, okay? And so you can see that because inductance, L, and mu are proportional to one another, then I can say that my inductance is actually just proportional to the slope of this BH curve, right? If I have steeper and steeper slope, that would mean I had higher and higher permeability, and therefore I would get larger and larger inductances. That's why really good magnetic materials with really high permeability can make really good inductors or really high valued inductors. But what happens when this slope starts to collapse? Basically, if I go to a magnetic field intensity that's just a little too high, I wind up with this slope starting to flatten out, right? And at some point, it completely flattens out and saturates. That's where this is called BSAT. It is the point where the magnetic flux density saturates, which basically means increasing the magnetic field intensity more and more does not continue to increase the magnetic flux density. We've basically saturated the core material. And what that means, as this slope goes to zero, it means the permeability of the material goes to zero. And if the permeability of the material goes to zero, that means the inductance goes to zero, right? And that's bad, because if you remember, and you should remember, the impedance of an inductor is J omega L, right? That's equal to the impedance of my inductor. If L goes to zero, I have a short, right? I basically have a short circuit right across the inductor. And that's not good, because that means that we're going to get infinite current flowing, because we have basically a short circuit. And so what we have to do when we design transformer circuits is we have to make sure that we are operating, when we're putting AC voltage across this this inductor, and we're basically, the current is ramping up on some part of the cycle and then ramping down into the negative part on the other side of the cycle. It's basically following this curve up to some point and then back down to some other point, and it's operating in between in this linear region where mu is fixed, right? Where the slope is constant. And that's where we have to operate. We could also operate up here, which would mean that we're basically just wiggling back and forth at some positive value. Or we could operate down here, which means that we're wiggling back and forth at some negative value. But if we increase our magnetic field intensity too much, we reach a point where the material saturates and we get no more increase in magnetic flux density as the magnetic field increases. And that results in mu going to zero, which results in L going to zero, which means this is a short. And that's not what we want, because that will result in very large currents flowing, can damage stuff in your circuit. It can also ruin certain magnetic materials. If you're not careful, you can basically permanently saturate them and the material won't magnetize anymore, and then it won't even be a good core material anymore. So this is a very big consideration. Again, this is purely practical stuff. So for the sake of exams and understanding, be able to do homework, I'm not going to ask you about this on anything, but this is good practical knowledge, and that's, pretty much practical knowledge is always good. This is good for interviews. This is good if somebody asks you about how a transformer works. You definitely need to keep saturation in mind, because there are practical limitations to all of these components. And that's going to lead us right into the next video, where I'm going to talk about the last little topic here, which is the frequency limits of transformers. Of course, they work with AC circuits, but they don't work up to an infinite frequency. There is a limit. Obviously, they don't work with DC. Even low frequencies, sub 60 hertz, they start to get worse and worse because you're moving closer and closer to DC. There's also an upper frequency bound on where we can use transformers, and I'm going to talk about that in the next video and kind of wrap up the module there. All right, so we'll see you guys in the next video.